We are now recording. Let's get the slideshow set up, and let me go over a couple of announcements. Nothing too major here, I don't think. Unless you're a volleyball fan, and then it may be pretty major for you. We have an excellent volleyball team. I had last year, and I believe it's continuing this year. And the NJCAA District, and I guess L/L means ladies and men, tournament is coming up this weekend, Friday, Saturday, and Sunday. I think that stands for National Junior College Athletic Association District. It's either L&M or the district we're in, or that's ladies and men tournament, and this will be in Boaz, Alabama. So if you happen to be driving by Boaz or live up that way, you can go over to, if you're not working too hard, go over to the school there. Which school is in Boaz?
Sneed State.
Say again? Sneed State. Okay. So it'll be at Sneed State Community College in Boaz. And hopefully they'll take it all. All right. I think I announced this to you before, but I'll go over it again. This is from a UAB postdoctoral fellow, Dr. Christina N. Mora. She wrote to Dr. Wilson here at Lawson that she is one of the newest cohort of merit scholars at UAB. I don't know exactly what that means, but it sounds pretty impressive. And she came across this 1-week summer opportunity for college students interested in biopharma manufacturing careers. Now, I take that to mean biological, pharmacological, pharmacy company manufacturing drugs. Okay? I thought one of your students might be interested in applying. A 1-week thing, they're paying you $1,000 to come to 1 week, and they'll pay your travel expenses as well. The application deadline is in January. She didn't say when, but she has a website link here that you can go to and find, I'm sure, all the information you need, or at least places that you can go to find out that information. Yes?
I make a copy of that. I forgot last time you set it up here.
What's that?
I just need to take a picture of it right quick.
This one?
Please.
Okay.
Slipped my mind last time.
All right. Now, all right, that's for things coming up school-wide, okay? Let's talk about what's coming up course-wise. Okay, we're in Chapter 2. We should finish this fairly quickly today, okay? And once we finish it, we'll be ready for the last lab in Chapter 2. And that will be the last 2 hours today. We're going to start Chapter 3, which is one of the, if not the longest chapter we have in the course. Okay, so we'll get started on Chapter 3. And then Thursday, we will have gone enough. I'm sure at Chapter 3 today, we'll be ready for the lab Thursday. So we have on Thursday 2 hours of class, 2 hours of lab, and then the last 30 minutes will be your Chapter 2 test. Yes?
How would the test look like?
Say this again.
What does the test look like?
Okay. The test is very cute. No, I'm sorry. Okay. It's a lot like the one. Yeah, no, not the first one. Most of the tests we had in 111. It's multiple choice mostly. I think there may be 1 or 2 calculations on it. I think maybe 2 calculations, maybe 1 or 2 fill in the blanks, and all the rest of them are multiple choice. Much more like the regular test in Physical Science 111. We're through with that. That first test was unusual because they had such terrible questions in the test bank. I had to piece them together and come up with some more reasonable questions. And then, but from now on, we'll be using mostly test bank questions, although I have rearranged a few things so you can actually do some calculations and stuff. So it'll be mostly multiple choice, 2 pages, mostly multiple choice. I think 2 calculations and maybe 1 or 2 fill in the blanks. Okay, mostly multiple choice. A lot like PHS112 tests, most of them. Okay, any other questions? So today, 2.5 hours of class, 2 hours of lab. The lab, I think today will be fairly short. We'll be doing parts of it. You'll be doing sort of on your own or in pairs, okay? And the second part of it we'll do as one big group, okay? So it won't take us very long to get the lab done today. So I think some of you might be able to leave a little early. Now, let's get back to some other issues here while I'm thinking of it. I have returned Lab 1. I hope everyone's received it. Okay, if not, I'll get it for you. Test 1, I'm still missing 1, 2. Okay, Test 1, so as soon as you can get those made up, I can get those back to everybody. Lab 2, I'm missing 1, 2. Okay, as soon as you can get those done and back to me, that is great. Lab 3, I'm missing 1. Okay, different person. So as soon as I can get that one in, I can give all those back to you too as well. And then today, unless some more people show up, we'll be missing 1, 2. Okay, because we got said 10 people here, but I see we have 13. Oh, there it is, 3 people. Yeah. All right. Hopefully some more will be coming in. All right. Any other questions? Anybody? Okay. We started this last time, Newton's law of gravitation. Gravity is a force between any two masses. It's just such an incredibly small force for small masses that they're never sensed. I can't feel the board pulling on my hand at all, okay? Because the magnitude of that force is so incredibly small. It's proportional to the product of the masses, and proportional to and inversely proportional to the separation distance squared, another inverse square law, okay? And because these are proportional, there is a proportionality constant, and that constant is capital G, usually called that universal gravitational constant, and it's 9.11 times 10 to the minus 11. I mean, some incredibly very small number, and that's why the force due to gravity is so small between small masses. Once you get the masses big enough, you get enough force to feel it. Okay? We did work out why the acceleration due to gravity was 9.8 meters per second squared, and the gravity provides the centrifugal force for orbital motion. The moon's orbiting around the Earth orbiting around the sun, all the other planets orbiting around the sun, the stars orbiting around the center of the galaxy. I mean, everything. Anytime you have circular motion on an astronomical basis, that's gravity that's usually providing that. Now, this was the slide I think we left off on last time, but I think we did at least begin to talk about it some. Okay? Just like swinging that rock around your head, gravity is like that string that keeps it going in circular motion. So gravity is always toward, this is our moon around our Earth, okay? Our Earth is always pulling the moon toward it, and indeed it is falling toward it, except it's going with a velocity in this way, and so therefore the acceleration, the force, which results in acceleration, is pulling the moon inward always. But as long as it's got that sufficient velocity this way, then this is just changing the direction. It's not changing the magnitude of the speed, so therefore the moon doesn't exactly circle the Earth, but it moves about an elliptical orbit. Sometimes it's a little closer to the Earth, sometimes a little further away, but it explains this circular type motion, centrifugal force. Orbital motion will cover it. Slightly elliptical. All right, any questions on Newton's law of gravitation? Okay. Before we move to Earth satellites then, let's do a couple of examples on Newton's law of gravitation. Now let's go back and show the, that's right, they didn't show the equation for it. So, yeah. You get the equation written down here for you. It's equation 2.12. You'll find it on your page 50. And here's what it is. Whoa, let me get my pen set up. Again, I forgot and left my glasses at home this morning, so it's hard for me to read. This is force due to gravity. I'm going to put F sub g so you'll know what we're talking about here. Is equal to, and here's that proportionality constant, capital G, universal gravitational constant, the product of the masses, M1 times M2, proportional to the product of the masses, and inversely proportional to the square of the separation distance, d squared they call it. Okay? Same one we used when we showed what the acceleration due to gravity was. All right? I have to get far enough away to read this. The surface of the Earth is approximately 6,400 kilometers from its center. If the mass of the Earth is 6.0 times 10 to the 24th kilograms, which is quite a big mass, of course, what is the acceleration due to gravity? Oh, we did that. Okay. That's the one we did in class. Okay? We've already done that. Example 220 is what would be the value of G if Earth were less dense with the same mass but double the radius. Okay? So, we're going to use the same figures here except double the radius. Well, the universal gravitational constant, and I think they gave it in the text, if I can read it, I'm sorry, I said 9.11, 6.67 times 10 to the minus 11, 6.67 times 10 to the minus 11, that's Newton meter squared per kilogram squared, that's the unit for it, times M1, M1 would be the Earth's mass, 6.0 times 10 to the 24th kilogram. Okay. Divided by now we're going to double the radius of the Earth. And before we were using 6,400 kilometers, so now we'll use 12,800 kilometers, but that's times 10 to the third meters, because everything we have is in terms of meters, not kilometers. Notice this is meter squared, but that is also squared. I neglected to square that. Just the denominator there, so it's a little sloppy on my part. Now, notice we've left out the other, and this, remember, was mass times acceleration due to gravity, and this is the mass of the object. Your mass, whatever mass you're doing, times acceleration, that's the other mass up here, and those masses cancel out. So your G for the low-density Earth, I'll put LDE, low-density Earth, okay? That would be 6.67 times 10 to the minus 11. Okay, let's take care of some of these units. A Newton, by the way, is a kilogram meter per second squared. So one of these kilograms wipes out one of those. This kilogram wipes out that one. Here we have a meter squared, there we have a meter squared. And what do we have left? Meters per second squared. That's going to be the acceleration due to gravity of the low density Earth. Okay? So that way we don't have to carry all those units around. Okay? 6.0 times 10 to the 24th. And the whole thing here will be meters per second squared divided by 12,800 times 10 to the third squared. Okay. So pull out your handy dandy calculators and start pecking away. 6.67 EE or EXP minus 11 times 6 EE or EXP 24 divided by 12,12800 EE or EXP. Back off a moment here. Be sure you open parentheses before this 1200. Okay? That stuff up there divided by open parentheses 12,800 EE or EXP 3, close the parentheses, and then square it. Squaring key. Okay, a little bit different from taking a picture. Okay. So, and then see what you get. Equal. Anyone got a calculator? And you can do it. Say it again.
In the numerator, that's 6 point what? In the second place.
This is 6 point. This is 6.0. Just 6 will do. EE or EXP 24. Anyone got it calculated yet? Give it a shot.
I may have hit them wrong pad, but it's like 359 million.
Okay. The numerical part isn't quite right, but is close, but the
It's got red in the
order of magnitude isn't. Did you square this thing down here?
Oh, no, I did not square the thing.
Ha! That may account for it.
I got 2.4.
Okay, 2.4 meters per second squared. Okay. I bet you when you square the denominator, it's going to come much closer. Okay. Any questions on that? So, we're 9.8. This is 2.4. That's about a quarter. Okay? So, you double the radius because it's squared. That's 4 times. So, you're dividing by 4 from what you had before. And that's just about right. All right, any questions? Okay. Now, I think before we go to Earth satellites, let's mention the blurb at the top of page 53, a closer look, and it says gravity problems. It's a pretty interesting little blurb there. It talks about astronauts doing spacewalks and working outside of a spacecraft up there in space. They're still influenced by the gravitational pull of the Earth, but it's so much less. The weightlessness is apparent, but they still have a little bit of weight, and so you have some problems related to that. Mostly physiological problems, okay? What goes on inside of us, okay? And here's Ethan. Now, one thing that really, that they've noticed big time is people start losing muscle mass because you're weightless. You're not having to support your body anymore. You just go and float along, you know. So people start losing muscle mass. Things like equilibria in your ears, you know, because there's nothing to let you know when you're upright or upside down, you know. Those kind of problems happen. Read that. You'll probably run into several more. But anyway, pretty good little blurb. All right, let's move on to Earth satellite. Here we go. Now, we mentioned part of this before. Artificial satellites must travel more than 320 kilometers above the Earth. Any idea why? Now, any closer than that, the Earth's going to suck them right on down. So they've got to be at least 320 kilometers above the Earth. But not only that, remember when we're talking about the moon? Let's get this out of the way. Okay, the moon has to have a velocity here, otherwise it gets sucked in. That velocity is what keeps, remember the centrifugal acceleration formula? Okay, mv squared over r. You have to have a significant velocity here to keep you from being sucked into the Earth. So not only do you have to be at least 320 kilometers above the Earth's surface, you must travel at least 8 kilometers per second to maintain your orbit. Otherwise, you go into a spiral and you crash. Okay? Now, 8 kilometers a second. A kilometer, that's about 4.8 miles per second. Can many of you run it quite that fast? Maybe not. Okay. Close, but no cigars. Okay. That's moving. That's hauling it. Okay. Now, the example they give here is GPS satellites. Now, this is true of GPS satellites. It's true of your communication satellite. Yeah.
Not to interrupt, but there was a thing on the news the other day where Samsung had a satellite fall out.
Oh, did it? Yeah. Okay.
Somebody's front yard.
Wow. Okay. And that was probably one of these communications. This is GPS.
It was kind of small, but
yeah.
They tried to say it was a soft landing plan for Earth, but
right.
It landed in somebody's yard, so anything could happen.
Yeah, it can. Our first attempt at a space station came down, and they were afraid it was going to hit in Australia, but it hit in either the Indian Ocean or the Pacific Ocean, one side or another before it. So that was way bigger than a Samsung satellite would have been. So they can still do some damage because they're coming down at a pretty hefty rate of speed. But these, your dish TV, direct TV, any of those kind of things, they have to be in what they call a geosynchronous orbit, meaning they have to be exactly at the right height and exactly at the right speed. Otherwise, they start moving. So, in other words, this satellite stays right over here, always. And this one's right over there, always. And this one's right over there, always. Okay? And all these others are up there for GPS purposes and all of your things that you fix something on Earth in place and you want the satellite to be right there. That's what it is. Now, for GPS, you have to have a good readable signal from at least 3 satellites. Otherwise, you don't know where you are. Okay? Because this satellite, all it will tell you is you're somewhere on that circle. This satellite tells you you're somewhere on this circle. And this satellite tells you you're somewhere on that supposedly circle. Okay? So, if you only had 2 pieces of information, you'd think, I'm either here or there, or here or there, or here or there. With 3, though, that's called triangulation. And that's how GPS, that's how your disk is only receiving signal from one satellite. But it still has to be in a geosynchronous orbit so that dish is always facing it. But these, to pinpoint GPS locations, you have to know exactly where you are. Now, anyone know how the GPS system came into play? How did it get started? U.S. military. I'm not sure, but I'm kind of guessing it may have been the Navy, because when you're out there at sea, like right here in the middle of this, it looks like Atlantic Ocean here, shooting stars and things like this give you something. But guess what? If you're alone out there, the horizon always looks the same. Okay? You can be tooling along, it never changes. There aren't any landmarks out in the middle of the ocean. So you have no way of knowing, no mile markers, okay? You have no way of knowing where you are exactly. Now they have what we call dead reckoning and other things. And we used to literally shoot the stars morning and evening just to pinpoint our location best we can. Because the stars are sort of fixed out there too. Of course, we're rotating in different things, so they'll be changing relative positions, not like the satellites here. But they came up with it first, and then I guess the government allowed commercial entities to use some of the data from it. Now, they say when we get within, I don't know, what is GPS good for? Anyone know? I'm guessing 10, 20, 100 meters or something like that. Maybe better or worse than that, I don't know. They say with the military stuff, you can almost read a license plate. I mean, it is precise. I mean, they got things down to an exact amount. Okay. Now, the next issue they're talking about here is weightlessness. Okay? And as long as you're that close to the Earth, you still have some weight. Okay? But you don't sense that weight because, as it says here, astronauts appear to be weightless, but are still affected by weight. Therefore, they can't be weightless. The astronauts are actually in free fall, just like the satellites are. They're always, because the Earth's turning, they're turning with the Earth, they're falling. Just like the moon is. The moon, if it's left to just its velocity, it'd be heading away from us. But the Earth is always pulling it to itself. Okay? So it's always in free fall. And so are the astronauts. If they're that close to the Earth, then they are falling to the Earth, but because they have the same velocity of the spacecraft, they are projected like this and the Earth is still pulling them in. They feel like they're weightless, but they are being drawn into the center of the Earth. But because they have that velocity, they're never getting there. They're actually in constant free fall. Do you know how the astronauts, not just astronauts, I know one company is SpaceX, but there's another one out there who is beginning to accept reservations for trips into space. Pretty expensive trips into space for very short flights, like $12,000 a seat or something like that. But how the people have to prepare for that sense of weightlessness. The astronauts would go up into a very fast jet aircraft, very, very, very high, and then it would dive, and they're actually sort of lifted off their seats, and they get this sense of weightlessness. But of course, they can't dive forever, so at the bottom it pulls out of it all of a sudden, and then they're pulling G's, many times more than the acceleration of gravity, and they call that aircraft the vomit comet, okay, because you tend to lose your lunch, Okay, and you go through that kind of.
I'm gonna be sitting very.
What's that?
I'm gonna sit in the very front. That way everything goes to the back.
Yeah. But remember, we're going downhill.
Yeah, you're doing right.
Yeah. No, you're right. Okay. All right. So they're never really weightless unless you get out into deep space where you're outside the gravitational field of just about everything. But we never get out there. We're always within our solar system, and so we're always revolving around something. And even our solar system is revolving around the center of our galaxy. So you have to get way out there in between galaxies before you're actually come close to weightless. All right. I think that's the last slide. There is one really neat people behind the science, a name we've used multiple times, Isaac Newton. If you're talking about motion, you're talking about forces, you're talking about acceleration, you're talking about momentum, you're speaking Isaac Newton's language. He's the one who came up with most of the concepts that we've talked about in this chapter and into the next chapter. Okay? Really interesting character, a really nice little blurb here. However, this cannot be your source. You can get information on sources from here, but this cannot be your source. You have to get outside the book to get your sources. And we'll mention this. It says Newton was born on January 4th, 1643, by modern day calendars, but actually by the calendar under which was in place at the time he was born. I think it was on Christmas Day of the previous year, 1642. But they hadn't updated the calendars yet, and we were drifting off our seasonal things, and they had to do some adjusting. But earlier in 1642 was when Galileo, if I'm not mistaken, Galileo had died. So it was there. He was born within a year of the time that Galileo died. There's a pretty interesting thing there. In many respects, he never should have lived, okay? He was so premature. Most kids that premature at that age didn't make it, okay? Because they didn't have, but he somehow managed and had pretty rough upbringing. His dad had actually died a month or two before he was born, so he never knew his father. His mother remarried. The guy didn't want to raise somebody else's kids, so shipped him off to a grandmother to raise. That was somewhat traumatic. The second stepfather died. His mom brought him back and decided he ought to farm for a living. He was not a very good farmer. He watched apples fall. That was about his extent. But anyway, he wound up at Cambridge. I think an uncle or somebody recognized his brilliance, sponsored him to go there. But he was a poor kid. And literally he had to be almost like a servant to the richer students there, washing their clothes, washing their dishes, shining their shoes, whatever, because he couldn't afford tuition, so he had to work his way through school. But on the academic front, within 3 years he had passed every professor there in any of the sciences of math. And the guy who was the chair of the math department resigned so Newton could take over. Okay, he was that brilliant. So quite an interesting guy. Seemed to have been not very likable guy. He fought with just about everyone, fussed and argued and stuff. He was also a politician, a member of Parliament. Really interesting character. All right. The summary at the end. Almost missed my favorite phrase. Nothing replaces reading the chapter. Okay? So if you haven't read it yet, shame, but go on and read it. Okay? please read the chapter, okay? You'll pick up things that I missed, that weren't covered in the PowerPoints. Please read the chapter. Then once you've read it, your summary here is a bit on the short side. It's reasonable length. But in the summary, a lot of the italicized words are some of the more important ones. I can't see them all now because I don't have my glasses on, but I see a few of them. Then the summary of equations. Last chapter, 1. This chapter, 12. And many of these can be rearranged in different forms, just like that 1 in the last chapter could be rearranged into 2 others. Most of these can be rearranged into a variety of other formulae. So, quite a few of those. Key terms, a fairly short list here, relatively speaking. They list them alphabetically, but they place the page number under which they were either first introduced or defined or described. Then, the applying the concepts. It's about average number of questions, 47 here. To me, this is the best study guide for the test. Okay? If you can do these 47 multiple choice questions, get close to the right answers, because they give the correct answers at the end of, after the 47th question. Don't look at the answers first. See if you can figure out what you think the answers are. Then go back and see how well you did. Figure out why you missed the ones you did, or if you can't figure that out, bring those questions to class and we'll talk our way through them. The book could make some mistakes there, okay? But a little more likely that we make mistakes. So bring the questions. I don't understand how they got this one. We'll see if we can figure it out. All right, after you work through those, questions for thought, there's only 12. This is fewer than most chapters, but they're important questions. For further analysis, there's 6. That's maybe 1 or 2 more than normal. But then, and unfortunately I don't think they have the answers, but the Group A and Group B, but the Group A exercises used to have the answers in the back, but I haven't found them in the new thin book. I specifically asked the lady who was quizzing me on it, please put the answers for the parallel exercise of Group A in there. She said, will do, and did not. So they're a lot like your examples that we did in class. And you see there's a whole passel of them, like 31, that you can work on. All right, any questions on Chapter 2? Today's lab will cover 2 major issues, forces, which includes Newton's 3 laws of motion, and at least 2 of them anyway, and also momentum. And that's what today's lab will deal with. All right. So let's get out of this, close it off, and go to Chapter 3. And if you'll notice here, I can't read this well. Actually, Chapter 2 was one of the longer chapters. Its PowerPoint presentation was 5,000, almost 5,500 kilobytes. Chapter 6 coming up will be 4,500. Chapter 3 is, well, a little over half of what Chapter 2 was. But it's still a pretty long chapter and covers quite a bit of material. The PowerPoint's just not as extensive. Energy is what is covering. What do we know about energy? Anything much?
Can't be destroyed.
It's what?
Transferred. It can't be destroyed, it's transferred.
Okay, energy cannot be destroyed, or it can be changed from one form to another, but energy is, you're absolutely right, energy as a whole can neither be created nor destroyed, it just changes its form. Now, there were probably several, I'm guessing, decades and maybe even close to a century where people really couldn't distinguish much between energy and forces. But there's some pretty big differences between them because they didn't have them well defined. Now we've got them a lot better defined, so we will be talking about this. We always refer to forces, but forces and energy are very different concepts. Related for sure, but very different concepts. What does this seem to be a picture of here? A wind farm is what they call it. Now, when we were, I don't know where this is, it doesn't look a lot different from what we saw. My wife had professional meetings in Salt Lake City or near Salt Lake City several summers ago, and it happened to be during the week in between our terms. So I got to go. And we took off a bit early in that week. She was over the weekend. So we took off early and drove through several of the states out there. We went to Yellowstone again. We love Yellowstone, but it was so crowded at that time of year. So we didn't spend as much time there as we wanted to. So we decided to just tour through some of the states. And I believe it was Montana or Idaho. When we were driving through portions of that, we would just see these farms, wind farms. Now, what was interesting was the farmers were down here baling hay, harvesting crops, doing other things. These things don't mess with that. I mean, yeah, you got a big pole there, but the blades don't come anywhere close to the ground. So it was, and you could hear the whirring when if you had the windows open, you could hear that whirring. What is it going on there? Well, the wind has, and we're going to be talking about this later, kinetic energy. You don't need to know what that is yet. And that kinetic energy is what's turning the blades. And then the blades are turning electrical generators. And that's generating electricity, and the electricity is being caught through wires probably running underground and shipped out somewhere. And this is producing these windmills here, and the others you see could be producing as much electrical energy as some pretty major coal-fired, natural gas-fired power plants, okay? And the fuel is absolutely free because the wind's blowing anyway, okay? So that's what's happening. We're converting the kinetic energy of the wind into electrical energy, and then the electrical energy can be used to produce light, heat, your computer generation, whatever, television, music, sound, anything. So energy is changing forms constantly. The total energy cannot be created nor destroyed, but it can be changed multiple times. Okay. Here's the core concept. Energy is transformed through working or heating, and the total amount of energy remains constant. Exactly what you were saying. Now, this is another way of energy transformation. This picture is in your text as well. The first one was similar to that one, but a little bit different. What is this? Can you tell? It's one of the dams. I don't think it's Hoover, but Hoover is I think a little bit bigger. I don't know if it's taller than this one, but it's a little bit bigger. But this is one of the big dams, probably on the Colorado River like Hoover is. I don't know that for sure, but it's on one of those rivers. What is happening here? Hydroelectric, okay? And what's happening, the dam is holding back the lake that's behind this. Here's the downside. The upside, the water level is about there. As the water falls from this level to that level, down these chutes, okay, it's gaining kinetic energy, the energy of motion. And that moving water is then turning turbines down at the base of the dam, and those turning turbines take that kinetic energy of the water, convert it to electrical energy, because those are also generators, and then the electricity is shipped off through these lines here. So here we have the change of potential energy, kinetic energy, electrical energy. All these changes are happening. The total energy is conserved, but it's changing forms constantly. Okay. So, it says energy is transformed through working or heating. We're going to talk about work in this chapter, and then we're going to talk about heat in the next chapter. Okay. Here is your fundamental law, the one that Logan was basically almost quoting there. And this is the conservation of energy. Almost exactly what he was saying. Well, they don't list the law itself. Basically, the law was pretty close to this. Energy is transformed through working and energy, but the total amount of it remains constant. That's the conservation of energy. Now, that's the fundamental law. These are manifestations of energy. Work is actually a form of energy. They use the same units, okay? Motion is a form of energy. The moving wind, the moving water, forms of energy. Position, the energy of position. If I were to take this book and have some very convenient feet right here for Diamond here, and if I were to drop this book on her foot right there, she would feel it, but it wouldn't be so awfully bad. But if I were to raise the book to here and drop it, would it be better or worse? It would be much worse. Okay, why? Different energy due to position. Okay, so we'll be talking about the energy of position. Outside, and today we don't have a lot that we still do, it just isn't as obvious, there's electromagnetic radiation. Okay, in other words, light. Still light outside, just a little overcast. Okay, that's a form of energy. And thankfully, those little green leaves out there, the ones that haven't changed yet, they are converting that light to what? Yes, to sugars, simple sugars, glucose, fructose, sucrose, some form of a sugar, and then the tree continues processing those sugars and makes them into complex starches. The wood is a very complex carbohydrate. The leaves are carbohydrates. The acorns or the seed pods, whatever, that's probably maple there. I know those are maples. Yeah, that's a maple too. The seed pods for that, those are stored energy in that. Quite often, oils, okay, would be. So the radiation, the light, is being transformed into chemical energy. We may take that wood and burn it. That transforms into heat energy. The chemical energy, after that wood and all sorts of other things have decomposed over centuries, millennia, then you have coal, natural gas, petroleum, that stored chemical energy. That energy then can be used for heat or other things. So there's just all these. Now, nuclear energy is the one that's sort of a little bit more bizarre. We didn't know we could do it until right around World War II. Remember the Manhattan Project? That's when they worked on how to harness nuclear energy. Not an easy process, not a cheap process, but they can do it. But nuclear energy, that's really where all this radiation is coming from. The sun. The sun is a huge nuclear reaction, okay? So that's where it all got started, was on the sun, and has made its way here to us. Mass itself is a form of energy. Wait a minute. Can that be true? I believe Mark, a class or two ago, gave one of the most famous formulas in physics. You remember what it was? E equal mc squared. Guess what the E stands for? Energy, right there. And what is M? Mass. So that tells how mass relates to energy. And it only takes a tiny amount of mass to make an enormous amount of energy. Because guess what C is? C squared? The speed of light, which is a very big number. An enormously large number, and then you square it. making it even bigger, you multiply that by that tiny amount of mass and you produce an awful lot of energy. That's what's happening with nuclear energy. Okay? A tiny amount of mass is transformed into energy. Okay, some of the sources of this, when those little green leaves fall to the ground, collect with other organic materials, get buried, biologically treated by all sorts of microorganisms and stuff, and lots of time, lots of pressure, lots of temperature, they ultimately change to petroleum, coal, okay? These are what we call the fossil fuels because they come from what used to be living plants mostly, but also animals. Then the moving water, as in rivers and stuff behind dams and that, that's a source of energy. Nuclear, of course, what is it? Wilsonville, is that a nuclear plant? One of the, maybe Wilsonville's coal fire, I don't know. But,
Alabama Power?
oh, yeah.
There's the one in Wilsonville, there's one out 22.
Is this nuclear?
Yeah. No, I'm about nuclear.
Okay, somewhere in the state there's...
Scottsboro's got a nuclear power plant. Scottsboro.
Scottsboro. Oh, wow.
It's
Okay.
not active anymore.
No, it's not.
It never was active.
They almost finished it in,
By the time 3 Mile Island happened.
and everything kind of.
Yeah. I wouldn't be surprised if someone might...
Somebody bought it for private, and they tried to get it going, but they hadn't done it yet.
Okay. Because I know the power plant in my home county in Georgia, in Burke County, Plant Vogel, it was up and running at the time of 3 Mile Island, but they left it running, and now it was the first one since 3 Mile Island, which was generation ago, that they actually expanded, and they're opening some new reactors still.
So where were the chemicals coming from that they were disposing of at the
There are two nuclear power plants out of the one in Decatur, the one in Columbia.
Okay. Columbiana, wow, that's fairly close. Okay. So there are some in Alabama, okay, in Georgia and other places. And then we have solar. The trees have been using solar energy for a long time, but now we're beginning to use it quite a bit more. And notice they didn't even mention moving air. That's now coming back into vogue as well. In the old days, we used windmills quite frequently to pump water or other things like that. So now they're coming back and we're using wind again. What are some of the uses? Well, the petroleum, and in some cases in the old days, coal was used for transportation purposes. Generation of electricity, petroleum, coal, moving water, nuclear, even solar, generation of electricity. Heating and cooling, of course, petroleum, coal, and through electricity, others. Cooling, same deal, and lighting, okay, through electricity mostly. Though we can burn oils or other things to provide light. We don't usually do that anymore. But those are some of the ways, multiple ways, that energy is changed, used, perceived. The list is almost endless, okay? So let's look at the first of those, work, okay? Work is a product of the applied force and the parallel distance through which the force acts, okay? Let me illustrate it with the chair here. Okay, if I apply a force to the chair, I'm going to push on the chair. The magnitude of that force times the distance through which I was pushing. Not after it left, but the distance at which I was pushing. The product of those two is the work I did on the chair. Or the product of the force due to gravity of the chair times the distance I lifted. That's the work I've done on the chair. Or dropped it on Diamond's foot. Oh no, I wouldn't do that. Okay. But that's all work. Okay? The product of the applied force and the parallel distance through it. Okay. I can push on the chair like this with the same force I did earlier, and is it moving? No, because the motion would be in that direction, I'm pushing in this direction, this is perpendicular, not producing any work at all, okay? Now if I push like this, I produce a little bit of motion. Why is that? Because the force, vector quantity, has a vertical component that does absolutely no work. The horizontal component is the only component that does work, because that's in the same parallel distance through which the force acts. So this guy picking up the box or the computer or the motherboard, whatever he is picking it up, here's the formula. Work is equal to force times displacement. Now that displacement must be in the same direction of the force, or the force in the same direction of the displacement. Now in the U.S. customary system, what do we use to measure force? What's the unit? Say again? No, that's in...
Oh, slugs.
No, slugs was mass that we use for force in the USA. Pounds, yes. And then what is our distance measure in the U.S. customary? Feet. So this is a foot pound. Okay? A foot pound. How about in the metric system or SI system? What's the unit of force? Someone said it earlier. Newton. And your distance is? No. Meter. Okay? So a Newton meter, okay, is a work unit, but a Newton meter has another name, and that's a joule. Okay? Not spelled like women's best friend Joule, but, you know, Joule, named after James Prescott Joule, who we'll mention later in the chapter and in the next chapter as well. So therefore, the symbol for this is capital J, because it was named after somebody. Foot pounds, there is no special name for it. You just call it foot pounds. Okay. But a force times the displacement. Foot pounds, Newton meter. Okay. And a Newton meter is a joule. And if you break it down even further, a Newton is a kilogram meter per second squared times another meter would be a kilogram meter squared per second squared. So that's another fundamental units of energy in the, or work in the US, in the SI system. And here we hit them again. The units of work and energy are joule, or Newton meter, or foot pounds. Now, here's a dumb story I tell. It's a true story, though. When my wife and I were looking at houses, this was several decades ago, we had been in a little two-bedroom bungalow, which we liked a lot, fit us nicely, but whenever we had company in town, it got pretty crowded fast. One bathroom, you know, that kind of stuff. And we had absolutely no trees in our yard. We had neighbors with trees, and we got some shade from them. We planted a few trees, but we just liked a little bit more, and my wife liked another neighborhood better, and we finally moved over to a different neighborhood and found a house we really liked. But one sort of problem with it, it was built on a hillside kind of, and they had flattened a certain place and built a house on that. And then the front yard went on down, the backyard went on up, okay? But then along came a couple of owners ago, and they wanted to expand in the back. They wanted to put a family room and a screen porch back there. So they did, but then they had to dig into the hillside to do that. And it made the house look a little squatty, but that was just appearances. That didn't bother me too much. But the thing is, that backyard, the water ran off the hill and just ran into the back of the house. And they used good, I'm sure, materials when they were building it, but I knew in time that hydraulic pressure constantly on that was going to cause some problems. So, and they put in the back of the den that they built back there little squatty windows, because the soil came right up to the bottom of the window. You know, you looked out the window and saw the surface of the soil right there. And that had very close to wood-to-ground contact, which is not a good thing to have in the South. Why?
It deteriorates. If the wood gets water, it deteriorates.
Okay, it will deteriorate for sure, and there are other things that will help it deteriorate faster.
Termites.
Termites, exactly. So I looked at that and I said, Karen, I know it looks a little squatty, but the main thing is we need to do some berms or something to get the water to run away from the back wall of the house, and also to get at the same time, lower the soil level there so that we don't have wood-to-ground contact. Okay? And she said, well, good. I wanted a patio anyway. Whoa, way more than the digging than I had in mind. I thought my idea had plenty of digging in it, not for patios. So that summer, we actually closed on the house on Halloween. The first year I worked here, we were then Bessemer State Technical College. Okay, so this was 20-some years ago. Okay, and that first year, I was a new kid on the block pretty much as far as faculty was, and usually in summer you didn't have full loads, and all the senior instructors, they got as close to full loads as they could get. I wound up with just 2 courses, and back then we were on the quarter system. And on the quarter system, what the automotive program did, they came to school 5 weeks, went to the dealerships 5 weeks. Same thing y'all do, 8 weeks, but this happened all 4 quarters, including summer. Now you do that just fall and spring, 8 weeks each, and then summer everybody comes the whole time, right? Okay, and you only have the one summer. Right. Okay, so I was teaching the automotive math classes, and they had pretty big classes, but it was only for the first 5 weeks of the summer. The second 5 weeks, I had just part load, 2 classes for 5 weeks. The rest of the summer I had off. Not getting paid, but it still was off. But I married money, so I didn't worry about that. Okay, so I had sometime, I only came 2 days a week for those part-time, okay, the first 5 weeks, but the last 5 weeks I spent digging out the patio, okay. And as I was digging out the patio, and this was with a pick, a shovel, and a wheelbarrow. Later we got Karen's dad's rototiller to help break up some of the really hard red clay, filled with rocks, okay? Do any digging in the area, you're going to hit rocks. And we did. And sort of about the middle of the patio, what was going to be the patio, I hit a rock. And it wasn't just a rock, it was a boulder. I mean, the more I dug, the bigger it got. And I got down to what was going to be our grade level, and it still was going down, but it was beginning to come in. It was huge, okay? I had hit other rocks, but usually I could dig around and get them out. We used it to build a retaining wall. But not this one, okay? This was enormous, okay? And so there were several days in there where I was doing nothing but digging around the rock. And I was using cheater bars and everything I could to try to budge that rock, okay? Now, it was hot, and I was sweating, and I was expending an awful lot of forces on that rock. But I could not budge it. Was I doing any work? No, because work is force times the displacement. I was not displacing the rock. But I didn't want anyone giving me physics definitions of work that few days in that week, because I didn't want to hear I wasn't doing any work. I was running and speaking up, well, never mind. But anyway, no displacement, no work. Okay. And that is so true. I don't know if you've ever watched some of those cheerleading competitions when they start doing all these pyramids and stuff like this. When those guys on the bottom are holding the layers above them up, are they doing any work?
I would say.
You would think so. Getting the people up there was doing work, but holding them there, that's not doing work. Expending a lot of force to keep them in place, yes, but technically, no displacement, no work. Okay. So, here's one example. If you take the book here and move it up here, have you done work on the book? Yes, because it was here, you displaced it here, there's your distance, there's the force. The force was the weight of the book. Whatever the book weighed, that was its force. You exert that, pushing, pulling, lifting it upwards through a distance, and that's work done on it. Now, if you had moved the book from here to here, were you doing any work? Technically, no, because you did not change its elevation. The only force on the book is gravity downward. So you have to do as in the previous definition, parallel distance through which the force acts. If you are doing perpendicular to the force is downward, you move it this way, no work's being done. Okay? Lifting it up, when the force is down, yes, you're doing work against that. Force times distance equals work. Okay? So, that guy out there hauling concrete blocks, a vertical distance, horizontal distance, technically doing no work. Even though he is exerting a force over a distance, that work is being done. It's only the lifting of the block that's doing the bulk of the work. Okay? Because you're lifting in parallel direction to what the force is acting. Okay. Now, to get a little bit fairer about it, if you slid the book down the shelf, you're overcoming a little bit of friction. Friction is in that direction, so you would be doing a little work. The work overcoming friction. Okay. Now, all right, before we get to simple machines, let's do examples 3.1 and 3.2. Now, the other thing I didn't bring today, I was leaving everything at home, is my watch. So someone keep me apprised. I know we're nowhere close to it now of when we get close to 3:45. Because at at 5:45, I'm still in Physical Science 111. Okay, and 5:45, that's when we stop the material here and start getting ready for lab. So, just don't let me go past 5:45. And if we need a break sometime, let me know that we can do it. All right, example 3.1, top of page 65. I have to get far enough away from the book to read it. How much work is needed to lift, so we are doing work because it's a lift, a 5-kilogram backpack to a shelf 1 meter above the floor? Now that's not quite this, but it's pretty close to it. Okay? So what we have is, got to get my pen set up. All right. Didn't take, did it? Okay, here we go. So here we have the backpack down here. There's the floor. And you want to lift it to a shelf that's 1 meter above the floor. Okay, here's the shelf. Okay, shelf back there. And we're going to lift it and put it up here. And this is a 5-kilogram backpack. What does 5 kilogram measure? Mass. That's your mass. So 5.0 kilograms, that's the mass of the backpack. What does the 1 meter measure? your distance. That's your distance, D. Can you answer the question just based on that? How much work is done? Now, remember in the last chapter, little w represented weight, which was a force. In this chapter, capital W represents work, which is a form of energy. So don't get those crisscrossed. They're two different concepts, two different entities completely. Now, I didn't mention this, but let me go on and mention it now. Force is a vector quantity. The weight on this thing is pulling it downward. Your lifting is pushing it upward. That's a vector quantity. Displacement is a vector quantity. But guess what work is? Not a vector. It's a scalar quantity. Okay? Now, I meant to ask this question earlier, back when we talked about foot-pounds. Have any of you ever used a wrench that was measured in foot-pounds? Were you measuring work?
It was turning the bolt.
Okay. And what is that wrench called? A torque wrench. You were measuring torque. And here's the difference. Work is, in foot-pounds, is the force and the displacement are in the same direction. But think about that wrench. The thick part, the distance part, is how far from the object that you're trying to twist are you exerting your force. That's a distance, but your force is perpendicular to that distance. So that's a perpendicular work force times the displacement. That's not work. That's torque. Torque is a vector quantity because when you do your force cross your displacement, the torque is upward. Okay? Work is a scalar quantity. This force times this force. If you got into vector mathematics, vector calculus, vector stuff, you would say that's a dot product which produces a scalar quantity, whereas your torque wrench is a cross product which produces a vector quantity. So that's why torque is a vector. Think about your engine in your car. Okay? Have you ever watched it when someone was revving it and you look at the engine? What is it trying to do? At least looking like. It's trying to come out of the oh, here's Latricia. Okay. And if you didn't have those motor mounts in there with those little straps on them, it would come flying out of the car. Okay? If those ever break, you're in trouble. Okay? If those motor mounts rust through or do something like that, that engine is going to start moving places because it has torque. That's a directed. That is a vector quantity. Work is a scalar quantity. Okay, so let's get back to our problem here. So work is a scalar quantity. And what's the product that work is? What's the formula? Force times the distance. It was on that last slide we were just looking at. Okay, I can see a distance here. I don't quite see a force. Is a kilogram a force? No, it's a mass. So how do we get the force that is required to lift that? Yes. The force here is the weight of that backpack, which is the mass times the acceleration due to gravity. Exactly that. So mgd, that will do it for us, because this is 5.0 kilograms. What's G? 9.8 meters per second squared. And what's D? Oh, I didn't put in my thing right, I don't believe. That is 1.0 meters above the floor. 1.0 meters above the floor. That just tells us everything has two significant digits. When you multiply those together, what do you get? 49. What unit? Second? These two would give you newtons. That would be Newton meter. And what's a Newton meter? Joule. 49 joules. Perfect. Okay.
The M and G.
What's that?
How do you get the M and G? Below the main, the second part.
Okay. I still couldn't hear quite what you
The M
said.
and G, how you get that?
Oh, the mg. That's the weight. That's the force that you're having to lift of the backpack. And that's mass times acceleration due to gravity. That was from the last chapter. Yeah, that's where that came from. Hey, guess what, folks? That last chapter, are we through with it? No, we're going to be using it throughout the course, okay? Over and over and over again. So this builds on itself. It adds to itself. Okay, so mg is the weight or the force that you're having to lift times the displacement. So that's where that came from. This gives you the right units. Kilogram meter per second squared, that would be newtons times meter joules. Kilogram wouldn't work there. There's no such thing as a kilogram meter. Doesn't give you anything meaningful. Okay. Now, 3.2. All right. Let me erase this one. Anyone need that a little longer? Okay. 3.2. How much work, so again, we're looking for work, that's our unknown here, is required to lift a 50-pound box. What's 50 pounds a measure of? That's a force, exactly. Unlike kilogram, which is a mass, okay? 50-pound box, vertically a distance of 2 feet. So there's your D is equal to 2 feet. So how much work is done there? What's work? We just did it. What is work? Help me. Say again? Force times a distance. And just plug them in. 50 pounds times 2 feet. And that will give you how much work? 100 foot-pounds. And that's your U.S. customary unit for work, foot-pounds. 100 foot-pounds of work. Okay. Now, the next thing in your text is power. But the next thing on the slide set, you have to go one page over, and these are your simple machines. So let's take a look at those. The basic premise here for these simple machines is the work in equals the work out. Now that's not work out like lifting weights or anything. The work in, the amount of work you put into it, it has to equal the amount of work you get out of it. Okay? Now, work is a form of energy. Therefore, if you got conservation of energy, you get the conservation here. In reality, does it ever quite work out this way? No, there's always some loss due to friction. You know, other, what did they call them before? Newton's first law, unbalanced forces. Any other forces that are not part of doing work. You never quite get all the work out of something that you got to put into it. It just never works out that way. But always some other work is being done against something else. So it does equal out, but it's just not useful work. Now, is force conserved? No. Okay? Let me put it this way. Can you lift a car?
Yes.
Yes? He's a strong dude,
You
isn't
can
he?
go stick a rack under it.
Okay? Not even hydraulically. Well, you can use hydraulic. Don't tell me y'all never. Yes, you've lifted a car with a jack. Now, what you've done there is you're exerting a small force lifting a big car whose weight is way more than you could lift straight out, or most of us could anyway. Okay? What you have is what we call a force multiplier. Okay? We also call this a mechanical advantage. And that's the ratio of distances. Because if you think about how much distance you're applying this small force and how much distance the car is going up, you're doing a big distance here for it to move just a small distance there. That's your ratio of this distance to that distance is the ratio of the force or the weight of the car you can lift here with this small amount of force you got there. That's what a simple machine does. Okay? Now, I don't know if you've ever been in a situation that you had to get, say, a motor or something way heavier than you can lift up onto the bed of a truck. Okay, you probably has happened. And probably what you did was put a ramp there. And if this motor was on a dolly of some nature, I bet you could push that motor up onto the truck. Okay? Because the weight of it is being lifted by the ramp, so to speak. You're just pushing it to distance. Well, that's an inclined plane. Your distance you're moving, you're pushing, your force is pushing, is a lot longer distance because the plane is this way. The height you're raising is whatever the amount is, okay? But the distance you're pushing is much longer than that. That's your force multiplier, okay? Now, this wedge is not what you did to your younger brother, so don't get off into that. Promise, okay? A wedge, this would be more like a maul, yeah, splitting wood. Okay, any of you get your fingers and go dig down into that and pull that wood apart? Not me, okay? But with a wedge, maul, what is the other thing? I guess you can just call it a wedge. You can hit that with a force, and basically, what is that wedge? Is two inclined planes back to back. And the distance you're forcing this way is very small compared to the distance you're driving that way. Again, a force multiplier. And if you think about what a screw is, screw holds a lot better than a nail, right? A lot tighter, a lot longer, okay? Well, what is a screw? A screw is an inclined plane wrapped around an axle. And that's exactly what you're doing when you're pulling things together with a screw. Same principle here. You're turning the screw a long distance to get a very short pulling power. A lever is sort of the same type principle. And we'll talk about three types of levers. But what are the elements of a lever? Does anyone know? The components. You need a fulcrum, okay? The fulcrum is the rock that I put down on the ground, and the pole is the lever that I was using to try to move that boulder, okay? And I tried to get this under, and I pushed and pushed and pushed, and still couldn't get the thing to do. It just sank the rock further into that hard red clay. I don't know how it did that, but it did. But anyway, I was using that. So we have a arm over here, long distance I was pushing here, trying to lift that a very short distance there. There's my force multiplier, the ratio of those distances. And a wheel and an axle. Okay, there's several ways you can think of this, but actually the wheel on your car has a diameter about like this, you know, whatever it is. The axle has a diameter about like that. It's turning revolution per minute. Same number of revolutions here. That ratio of the distances is your force multiplier. And then, of course, pulleys. Okay? Now, there's two types of pulleys. If I just have, again, I've asked this question several times. Have any of you been to McLean Science Center? Yeah, I'm talking about, okay.
Yeah.
You know those places over there where you can sit on the seat and turn a wheel and lift yourself? Okay? Some of those are fairly easy and some are quite hard. And the reason is, what kind of force multiplier do you have? If you have a pulley, you just got it hooked to the ceiling there, and you're trying to lift something, you have to exert the same force because the thing you pull is the same distance that goes up. You have to actually lift it. No force multiplier at all there. But if you run that through here and then down through one here and back up again, and that's what you do, for twice as much rope as you pull here, it lifts half the distance there. There you have the force multiplier. And if you run it around there twice, it's 4 times. And that's what, when you're on that thing at McLean Center, you are the one that's easy. You can turn that wheel. Of course, you're turning it a long way, but lifting yourself pretty easily. When you're doing that, and you're turning it much, much harder because of the force multiplier. So that's what a pulley is. If a pulley goes through the bottom, a pulley at the bottom, then you've got one that you have a force multiplier. It's just changing direction, no force multiplier there at all. Okay. The principle here is work in equals work out. The work in is the force in times the distance in equal force out times distance out. You're jacking up the car, your force in, okay, how much force can you exert? Strong people use 100 pounds of force, maybe even more, okay? But if you do it a long enough distance, like a foot, then that would give you 1,200 pounds out if it's only raising it 1 inch, okay? So here with 100 pounds of force, you could have, the out would be 12,000 pounds that you could lift, okay? I'm sorry, 1,200. Extra zero there. 1,200, which comes pretty close to what some cars are. Okay. Now, here's what we can do. Divide both sides of this by distance in. Okay? No, divide both sides by distance out. Now you have a ratio of what you jacked in to what the car is going up, the output. That's your force multiplier. So a very small force here could lift a very large force there. And there you have it. Force out equals that. Okay, they're talking backwards from what, okay. Force, distance in times force in. This ratio, if the input was several feet for every inch, then that's your force multiplier, and you can lift something with a very small force here many times, 12 times, 24 times, whatever. Archimedes, way back, 200 to 400 BC, sometime way back there, he knew about levers. And he said, give me a long enough lever and a fulcrum I can put it on, and I can move the world. Okay? Supposedly he said that, and that's absolutely true. Of course, levers are long that long and working, you put a fulcrum to do it. But if you did, if you could, that would be it. Now here's a gal trying to lift 300 pounds. Does she look like she can do 300 pounds? Look at those arms. That's pretty strong. Huh? Yeah, she's got good leverage. Leverage comes from lever. Okay. And what? Oh yeah, her form isn't great, is it? But she's pushing down with only 60 pounds of effort, but she's pushing down 2.5 feet. That's her effort distance. That's the distance in, force in. the distance out, she can lift that 300 pounds half a foot with that, with the fulcrum over here, and as long as this ratio and that ratio of this to that, same as ratio of this to that, because it's a 5 times here, she can lift 5 times the force here, force multiplier of 5, because her distance, 2.5 to 0.5, is a 5 times distance ratio. Okay. So that's an example of a lever simple machine. Now, they did several other things, and they used the term mechanical advantage. We're not going to go into all this, but they do have here 3 types of lever. Okay? The first class lever is the one that you, basically a seesaw. Okay? You have the fulcrum here, you put the effort there, it lifts there. I was always the grammar school heaviest kid in the class. I was in a very small class too. But, you know, I get down there, the other kids was up here and we could seesaw. I'd have to push to get him to go down, you know. So that wasn't much fun. Okay, so that is a first class lever. A second class lever is, I put the effort here, the fulcrum's down there, the load is in the middle. What's the illustration of that second class lever? Say again?
Deadlift. So picking it up from the ground.
Yeah.
Deadlift.
What do you call it?
Deadlift.
Deadlift. Okay, that would be if I was lifting it just like this. But if I were back here on the lever and it was halfway and the fulcrum was there,
Oh, you're like wheelbarrow.
wheelbarrow, that's exactly your second class lever. Okay? Now, there's another one, and this doesn't seem like it makes as much sense, but it does. If your effort is here about halfway, fulcrum's down here, and your load is out there, what's that?
Shovel.
That's a shovel, okay? You're not lifting as much as your effort is, but you're throwing it a longer distance, okay? So you have a negative or a small mechanical advantage there, but you can move it a longer distance. Okay. All right, now turn back a page, and we're going, we're going to start on power. Now, just a little bit of flashback here for you. One of the first things we talked about in chapter 2 was, in dealing with motion, displacement. Okay, and what was the first thing we did once we got distance or displacement down? What did we say we did to it? Divide by time. Time rate of change of displacement was what? Distance over time. Miles per hour. Miles is distance. That's velocity or speed. Okay? So we did a time rate of change. Then once we got a velocity, guess what we did to that? Divide by time again. Time rate of change of velocity is called then acceleration. Perfect. Okay? And then we have Ryan. Okay. We're only, we got everybody here then, don't we? Perfect attendance. Way to go, folks. We were missing 3, and Latricia came in, or Ethan came in, Latricia came in, and now Ryan, so we got everybody here. Good to see. Okay? So we wound up with time rate of change of velocity. That's an acceleration, another very useful quantity. Now remember I said there was also this concept called momentum, we did in the last chapter, which is the time and the time rate of change of momentum. Anyone remember what that was? Momentum being mass times velocity. Time rate of change of velocity was, you said it.
Time rate of velocity and acceleration.
Acceleration. So mass times acceleration is what? Force, exactly. Time rate of change of momentum is a force. So just about anything we come up with, let's turn around and do a time rate of change of it. So guess what we're going to do now? We're going to do a time rate of change of work. The rate at which work is being done, rate is usually time rate. The rate at which work is done is the rate at which the energy is transformed or expended, and this is power. It's equal work divided by time. Okay? And here is a good old animal here. He's exerting a force of 550 pounds, lifting this block 1 foot. And guess what? And it took him 1 second to do that. Guess what his power was? 1 horsepower. You got it. Very good. 550 feet, foot-pounds per second. That's a horsepower. We'll get to that a little bit later. Okay. That's the closest thing to having a unit of power in the English system that we have, the U.S. customary. We're going to go to metric though, and that's a lot maybe more familiar. Okay. Now, let's go back to my digging in my backyard. Okay. I worked for those, not continuously for those 5 weeks, but for most of those 5 weeks, we didn't have nearly as much rain as I wanted that summer. I could have gotten to stay inside one day. It was hot and dry, and that clay was hard, so there weren't many rainy days I got to miss a day, but I didn't do much on Sunday, I'll say that. But most of the other days I was out there, good portions of the day, digging in that patio, okay? And after 5 weeks, I'd had about half the patio done. And it was getting close to Labor Day, and on the quarter system, that 1st of September is about the time we went back to work. And Labor Day was early that time. And we said, hey, no way, once I get to working full time, I'm not going to have the time to dig this anymore. What are we going to do? Well, the reason I was digging in the first place, number one, I'm cheap. But number two, there was no room to get a bobcat in there. Okay? Because the house was here, the trees were there, there just wasn't room to maneuver a bobcat. So that's why I was digging pick, shovel, and wheelbarrow. Okay? But by the time I got about half the patio dug, there was no room for a bobcat to come in and work because I had a nice area there dug out. And we decided to go and hire one. This is a big old bobcat too, almost too big for the space we had, but he was good at it. So we hired him to come in, and in 1/2 of a day, he moved as much soil as I had moved in 5 weeks. What was the difference? The work done? The work was the same. I moved half the soil, he moved half the soil. I will say this, I moved it further than he did because I was putting it where I wanted it. But he was just piling it up, and I later had to move it again. But he dug half of the soil, I did half of the soil. We did the same work in that sense. Well, yes, the power, because the time it took me was a bigger time, which means I had a lot less power. And that bobcat, like I say, it was a big one. I think it was at least 250 horsepower. And at my peak, I'm way less than half a horsepower. So there was a big difference there in power. Work, no. The time, yes. Power, yes. So power depends on work, energy, but it also is inversely related to time. Okay? And that's where that comes into play. All right. Now, so power is the rate at which work is being done. So that would be work per unit time. That was the formula on the last one. Another formula there, a real good one. What are the units? Let's go back to this. What's the unit for work? The units for work? Joule per and time? Second. Now, the term joule per second, that has a name in the SI units. Anyone know what that is?
Is it a watt?
It's a watt. A what? A watt. A what? A watt. Okay, yeah. It's a watt. What? Okay. All right. So it's a watt. Okay. Named after, capital letter, James Watt, a Scottish engineer, scientist. He did a lot of the work on the original, well, actually, he's the one that came up with the name horsepower, okay? So he did the early work on power, but that was before the SI system was being used in England anyway, and in Scotland. So he came up with that quantity. So they named the metric unit of power after him, watt. Now, again, don't confuse parameters with units. These are your parameters. Power equals work divided by time. Power equals energy divided by time. These are your parameters. Your units for work is joule, time is second, the unit for power is watt. So don't get this W, that's the parameter, mixed up with that. You always have a number in front of this one, not in front of that, okay? So this would be 10 watts, 15 watts, 450 watts, whatever, okay? Whatever, okay? And you'll have numbers in front of these too. These are your parameters, okay? So the unit in the SI unit, the unit for power is watt, which is joule per second. And in the US customary, it's a horsepower, but that's not a foot-pounds per second. That's 550 foot-pounds per second. Now, how did James Watt come up with that unit? He said, what is the amount of work that an average dray horse, those are the big old horses like the Clydesdales or something, could do in a day, okay, on average. And that came out being 550 foot-pounds per second. Multiply that by the work day, and you get quite a bit of work, okay? But that's a power measure because it's how much work in a day, okay? So that's what horsepower is. Now, Thursday's lab that we'll do 2 hours in for the next 2 hours, and it won't take us 2 hours, will be walking versus running upstairs. And we are actually going to go to stairwells, and you're going to time each other walking and running the stairs. So get beefed up for Thursday's lab. Okay. All right. Now, let's go back to this formula here. And remember what we like to do with formulas sometime? Move them around. So how could you change this formula? What would be the first thing you would think of doing?
What is time times power?
You got it. Multiply both sides by time. That gets rid of the time here, and you get work is equal to power times time. Okay? Now, once a month, anyone who uses electricity is going to get a bill. Okay? And what do we usually call that bill? Yeah, we call it the power bill. Does that mean you're paying for power?
The usage, how much you use that power.
Okay. And what are you actually paying for? Have you ever paid attention to what you're actually paying for on that bill? You're not paying for watts or kilowatts. You're paying for, go home and look at your bill, kilowatt hours. Kilowatt is a measure of power, hour is a measure of time. That's what you're paying for. It's not a power bill, it's an energy bill. You're paying for the energy you're using. Everybody calls it the power bill. Why? Because Alabama Power Company sent it to you and they billed you, okay? But it's actually an energy bill, okay? All right. So the power bill you pay for energy. You don't pay for power, okay? Because you're paying for kilowatt hours. Power times time is energy. Now, here's the lab we'll be doing on Thursday. Okay. And you don't have to look this tired going to do it, but if you were to walk up these stairs pretty slowly, carefully, and all that kind of stuff, how much work are you doing? Your weight is the force and the height that you're going up. The horizontal distance, you're not doing any work. How's that? Perpendicular to the force. The vertical distance is what you're doing. So whatever his weight is times the height of the stairs, that's the work he's doing. Now, his twin down here, Mr. Energy, he is going up really quickly, but he is exactly the same weight. What's the difference in work? There is no difference in work. The work is exactly the same. What's the difference? He's taking more time, less power. This one's doing smaller time, more power. Okay? This one has more power. The weight, the mgh, the weight, mg times h, the distance, exactly the same. But the power is that work divided by time. mgh divided by time. If it's a very large time, it takes them a long time to go up there, very low power. Short time to go up there, then much higher power. So this is another example of power. The Bobcat and me, or walking versus running the stairs. Make sense? Okay. All right. Now, they have another pretty good illustration in the book. I wish they had on the PowerPoint, but they don't. A horsepower is 550 pounds of force lifting, this is 550 pounds, 1 foot in 1 second. Whereas a watt is 1 newton. That's what a newton would be compared to 550 pounds. A newton lifted 1 meter, which is further than a foot. They don't draw the arrow well here. The distance here would be about 3 times, a little more than 3 times this. But this weight is way, way, way heavier. You could easily do that. The horse could do that, okay, in 1 second, okay? Now, because you see, a horsepower is a lot of power. A watt is a fairly small amount of power because a newton is a fairly small force. A pound is heavier is more force than a newton, okay? And it's heavier, that's the correct way to say it. So a person could easily do 1 watt of work, whereas it would take 1 horse to lift 550 pounds 1 foot in 1 second. Okay. So let's go back and let's do example 3.3. Okay, y'all keep up with time for me.
5:10.
It's what?
10 after 5.
10 after 5. So we got about 35 minutes. Okay.
Let's take a break, man.
You want to break first?
I do. I can't speak for everybody.
Okay. You want one now? This is not a bad time for it. We've been at it for an hour and 45, 50 minutes, something like that. So let's do a quick break. We have just covered enough material for the lab on Thursday. So now we're moving into stuff that we'll be doing probably on the lab on next Tuesday, a little bit. Okay, yeah. All right, but we didn't get to work the problems. So let's do example 3.3 on page 68, I think that is. An electric lift can raise 500 kilogram mass. They just gave you what it was, wasn't it? The mass is 500.0 kilograms. Okay? a distance of 10 meters. So there's your distance, 10.0 meters in, I believe that's 5.0 seconds. So that's going to be your time, 5.0 seconds. Okay. What is the power of the lift? So what we're looking for is power. That's the unknown here. What is power? What's our formula for power? Oh, it was so long ago.
It was, power equals the work divided by
Work divided by time. Okay, we got, ooh, I don't see work up here anywhere. What in the world is work? Let's go back another step. What's work? This is from force times the distance. Force times the distance. Okay, over time. Well, I got a distance there, but I still don't have a force. What's a force?
mass times gravity.
Okay, mass times acceleration. And what acceleration are we overcoming here? Gravity. So that's mg d over t. Well, I got everything but g, but we know that, don't we? G, we knew, don't we? Okay. What units are we in? What units are we in? Kilogram, meters. They're good units, right? Right. SI units. So, what would be my mass? 500 kilograms. G, ooh, let me move this over so didn't leave enough room. $500 kilograms. That's your M. What's your G and SI units? G, we ought to know that. 9.8 meters per second squared. And what was our distance? Right up there. Distance we lifted it. 10.0 meters. And we're going to divide that by 5.0 seconds. Okay. Now, let's deal with the units first. A kilogram meter per second squared is called a what? Kilogram meter per second squared is a, Sir Isaac? Newton. That's a Newton. A Newton meter is a oh, come on. Joule. And a joule per second is a what? Watt. Yeah, okay. All right. So we're going to come out in watts, a good measure for power. So pull out your handy dandy calculator. Oh, we don't need a calculator, do we? 5 will go into 500 100 times. 100 times 10 would be 1,000. That would be 9,800 watts. Okay? Now, if I wanted, because that's a pretty big number here, if I wanted a smaller number but a bigger unit, what would I choose? Smaller number, bigger unit. Kilowatt. How many kilowatts would that be? 9.8 kilowatts. Now that's what I got. Let's see what the book got. I can't find it. 9.8 kilowatts. Good for them. Okay? Now, ooh, we're going to have to step back a little bit. Go back to page 66. Okay? They did a little stuff there, the slideshow didn't show it, so I sort of skipped right on over it. I was looking at the simple machines at the top. They have a few conversions there. I can hardly read them because I don't have my glasses on. Here's a few. We just used one. 1,000 watts is a kilowatt. We know that one. 1,000,000 watts would be a megawatt, and that's what they measure power plants in. Also atomic bombs, okay? And then they give us a few other conversions here. Well, they don't really, do they? I thought it was here. I know that's in here somewhere, but my eyes are, without my glasses, I can't find it. Okay. Yeah, there it is. I see it now. Next to the last line, first column, page 66. I knew it was on there somewhere. It takes about 746 watts. 746 watts is approximately equal to 1 horsepower. So a horsepower is a way bigger unit than a watt. But it's a little bit less than a kilowatt. So this would be 0.746 kilowatts would be 1 horsepower. So a kilowatt is a little bit larger than a horsepower. It takes only about 3/4 of a kilowatt to make 1 horsepower. So those are way closer to being equivalent to each other. All right, let's go back to our problem we just did and use that conversion. And it said the power that we have here was 9.8 kilowatts. So what we'll do is multiply this by blank blank to equal blank horsepower. Okay, this is a good old conversion problem. What unit will we go? Well, okay, the first blank, remember, is for your numbers. Don't mess with them yet. The second blank is for your units. Always put the units in the place. So what unit goes where? One goes on top, one on the bottom. Between kilowatt and horsepower. Which goes where? Always put the units in the place. One unit on top, one on bottom. Which goes where? Multiplying here, equaling there. All right, I don't think it's that hard. What unit goes where? One goes on top, one on bottom. Between kilowatts and horsepower. Okay, if you put kilowatts on top and horsepower on the bottom, then you get kilowatts squared per horsepower. That's not a horsepower. It's not going to work out, is it? So guess what we might do? Oh, the eraser didn't work. There we go. If we put kilowatts on the bottom and horsepower on top, now the kilowatts cancel out, which is exactly what we want to happen, and horsepower winds up just where we want it. So now that we got the units in the place, what numbers match where? Look up at the top of the page. Top of this. Right there. Match the numbers with the units. 1 horsepower equals 0.746 kilowatts. So you take your 9.8, divide it by 0.746, and what do you get? Anybody?
13.1
horsepower. Okay, I think they probably just round to 13. And the reason for that is you have 4 significant digits there, 3 here, but only 2 here, and then the 9.8 was only 2, so we're just going to use 2 significant digits, so you throw away the 0.1. 13 horsepower. That would be the rating of that electric lift. Okay? Any questions on that before I erase it? Everybody got it? All right. Let's erase that ink. And let's do example 3.4. A 150-pound person. What in the world is that a measure of? That is a force unit. Okay, perfect. It's also the weight, so I'm going to put F sub W. Runs up a 15-foot stairwell. That means a vertical lift of 15 feet. So what would that 15 feet be? Distance. Okay. In 10.0 seconds. What's that a measure of? Time. Okay. All right. What is the horsepower rating of the person? So how do we get power? That's what we're looking for. Power is equal to work divided by time. But what is work? Force times the displacement divided by time. And we got all 3 of those. Your force is 150 pounds. Our displacement is 15 feet. And our time is 10.0 seconds. Okay? If I'm not mistaken, that's 22500, 22,500 foot-pounds divided by 10.0 second. So that would be 2,250 foot-pounds per second. Okay? That's how much power the person expends in foot-pounds per second, but how do we get that to horsepower? Do you remember the conversion there? I'm going to do this one backwards because I'm running out of room. I'll put my blank blank here and blank horsepower here. Now these first blanks are for numbers, don't worry about those yet. Let's get our units here. What you reckon is going on top, what goes on the bottom? This is the multiplication, this is equal over here.
So is foot-pound per second, is that also watts?
No, it isn't. That's a SI unit. This is a U.S. customary. It's its own unit, foot-pounds per second, and it goes on bottom. And horsepower on top, and does anyone remember what a horsepower is in foot-pounds per second? Or how many foot-pounds per second in a horsepower? Which way? 550 foot-pounds per second is 1 horsepower. So we take this number here, 2250 divided by 550, and what do we get? 4 point what? 09. I think that's probably going to round to 4.1, right? Because you only got 2 significant digits there. So let's see how the book did. Whoa, 4.1 horsepower. Good for that. 0.41, I'm sorry. 0.41. Oh, that's what you said, and I wrote it down wrong. Oh, I think that's what you said, wasn't it?
What we went wrong is the 150 times 15. It's supposed to be 2,000.
Oh, yeah, I'm sorry. I did that wrong. Okay. This was the 20. Yuck. Nope. Goodness gracious, I can't get this pen to work. Okay. 2250 there, divided by 10, that gave us 225. I thought that seemed way too big. Okay. All right, and then divide that by 550 and you get 0.41. Yuck. I can't get my pen to work. There we go. 0.41 horsepower. Yeah, about half a horsepower. And that's a little more than half, less than half a horsepower. And that's about normal for a person. If a person can do 4.1 horsepower, I want to mess with him, okay? Don't even want to come close, okay? So, 0.41 horsepower. Good deal. Except for dumb mistakes here. Got it down? Good deal. All right, so now we move to motion, position, and energy. Well, we've been talking about energy all along, but mostly in the form of work. Now we talk about other forms of energy, okay? And this is 3.2. That was one long section there, 3.1. That was page after page after page. Now we're in 3.2. And y'all are keeping up with the time for me, right? Okay. Huh? 5:35. 10 more minutes. Oh, shucks. Okay. So motion, position, and energy. Here are a few definitions. Work and energy are related. They're first cousins, twice removed. No, they're related. In fact, they're the same thing. They're two manifestations of the same thing. Here's one definition. Energy is the ability to do work. Okay? When I was out there digging on the patio, the energy I had from eating as much food as I could get in me, okay, gave me the ability to do work. Okay? So energy is the ability to do work, but said the other way, work is the process of changing an energy level. Okay? I was changing the energy of that soil packed in the ground there into the wheelbarrow down around where we were going to put in our azalea bed. So, work is the process of changing an energy level, whereas energy is the ability to do work. They're measuring the same thing. Okay? So next, what is the relationship between work and the energy associated with position? The energy associated with position. We're not going to mess with motion yet. We'll get there in a bit. But we'll deal with what is the relationship between work and the energy associated with position. I've already sort of demonstrated that a few times. If I lift this book, which has a certain mass, times the acceleration due to gravity, that would give me the force I have to exert to lift it. That's the weight of the book, by the way. That's how much I have to do to lift it. If I change it from this level to that level, I've given it more energy because I've worked to change the energy level. Remember, Diamond's foot, you know, as I lift it up, it's going to hurt more if it falls. I'm not going to lift it up. Maybe. Okay. So, that's the relationship between work and the energy associated with position. Then we'll also talk about the relationship between work and the energy of motion. So work and the energy of motion, that's going to be a difference. So these are the next two topics coming up. We're first going to deal with energy associated with position and energy associated with motion. Okay. The first of these is called potential energy. Okay? The one I've been describing to you is specifically gravitational potential energy. If I'm lifting the book from here to there, I'm working against gravity. Because gravity is trying to pull the book down, I'm working against gravity. That's gravitational potential energy. That's what they're mentioning here. There are other forms of potential energy. Those little green leaves out there are taking the radiant energy from the sun, the light, and converting that to chemical energy. Storing the sugars, making the sugars, and storing them in the plant. Okay? So there are other kinds of potential energy but this is gravitational potential energy. So what we're measuring now, what we were calling D, we're now call H because that's the height. But in order to measure a height, we've got to have a reference. Where are we measuring from? If I'm measuring from the tabletop, then that's my reference level. Measure how far I lifted it in feet or in meters, okay, times its weight in newtons or in pounds, or the pounds are in newtons, and that would be my reference level. But here, it may be the floor is my reference level. Or if I went and hung it out the window, the ground may be the reference level. Or I might want to count sea level as my reference level. Okay? So you have to first determine, before you can determine how high it is, you need to figure out what your reference level is. Now, I'll often call this the zero reference level. And what we mean by that is, what I mean by it usually is, as low as this can go in this given problem. And since I'm not going to hang it out the window, I'd say the floor was my zero reference level. I'll measure everything relative to the floor. Now, if it couldn't go any lower than the desk, then I'll use the desk as my reference level. Okay? You get to choose your reference level. Okay? Now, there are other kinds of potential energy. I mentioned chemical potential energy. There's also elastic potential energy. I think I've asked this question before, but let's see. What does elastic mean?
The ability to bounce back.
The what?
The ability to bounce back.
Okay, very good. It's to return to its original shape. Okay? So we usually think of it as something that will stretch. It's only if it returns to its original shape. I've had a few things stretch before and not return to the original shape. That's not elastic, even though it's stretched to begin with. Okay? But yeah, the bouncing back, coming back to its original shape. Okay? So that is elastic or spring potential energy. Now think of that this way. If there's a spring attached to the wall here, and I go to pull on the spring, okay, I'll feel a little pull back against me, okay? And I'll pull a little further, it's going to be stronger against me. Further and even stronger. Or compressing the spring. Compress it a little bit, it's pushing back. That's returning to its original shape. Compress it harder, it takes more, and it's pushing back harder. Okay? So that is spring potential energy. Associated with position. How far from the equilibrium position you were. Okay? Electric charges deal that way too. If you had a charge here, do you want it to be positive or negative? I don't care. Negative. Positive? Okay, a positive charge here. And I come with another charge here. What kind do you want this to be? Negative. Okay, and if I bring it here, what's that positive charge going to do to it? Try to pull you to it, because unlike charges attract each other. So I'm going to have to hold it back here to keep it from charging into the positive charge, right? So I'm having to do work to keep it in this position, or it's doing. If that was a positive charge, then I'd have to be forcing it, doing work to get it to change its position. So you also have electrical potential energy. Chapter 6, we'll be talking about that. Now, work can change the potential energy. The gravitational potential energy, the spring potential energy, or the electric potential energy. Work can change the potential energy.
542.
540 what? 2, okay. Now, here they've been talking about potential energy. This bullet should be on the next page. Kinetic energy can change into potential energy. What in the world do we mean by kinetic energy? Movement, the energy of motion. That is kinetic. Kinesiology is the study of motion. So this is energy. So what if I were to take, I'm not going to do this, but take my book here and have a tennis racket here and swat my book, okay? Then the kinetic energy of the tennis racket could change the potential energy of the book. That's not what tennis rackets are for. But you could do the same thing with a spring, or you could do The same thing with that charge there. Whop it here and make us change its potential energy. Okay? This should have been on the next page. Okay. How about less stopping right there? We'll pick up with this figure on page 69 next time. Okay? So I'm going to pause. All right, not a lot to read on this lab, but let's hit it anyway. On the bench tops here, you'll see 7 100-gram masses. That's far enough when I have to read it. 100-gram masses on pieces of paper. Okay? Now what I want you to do, there's what? 13 people here, 2, 4, 6, 8, 10, 12, 13. 13. So every 2 of you pick one of you going to have one by itself. What I want you to do is take the piece of paper and then with a very quick horizontal pull it and describe what happens to the mass. So it's split up in pairs. One person will be without a partner. There's 3 over there, 4 over here. And yank on the paper. Yeah, I don't have anything. Be sure you pull horizontally, really quick, and describe what happens to the mass. Okay. What would you say is happening to the mass? Okay, what would you say basically the mass is doing? Staying in place. What property of matter does that demonstration illustrate? Did everybody feel like it stayed pretty much where it was?
No.
No? Let me see you do it. Horizontal pull. Pretty close to where it was, wasn't it?
Yeah, but there was still some displacement when it didn't stay there.
Not much displacement at all.
I mean, not much of none.
Yeah.
You just
Well,
asked me my observation.
Okay, yeah, but you can write not much. Okay, that's fine. Okay? Why? What principle of matter does that illustrate? Inertia. Perfect. Okay? Now, I forgot to type in one line here. There was one more question. And if you could write the question up above the first one, it's sort of out of place, but it fits up there, and say, which one of Newton's law does this come closest to representing? Newton had 3 laws. Which one does this come closest to representing? It was often called the law of inertia. Which one was that? Got your books, you can look. Anyone remember? In other words, an object that's at something continues to stay at rest, which is what these blocks did. Which law was that? First law. Excellent. So somewhere on there, write first law. All right. Now, everybody has written down. You wrote what your observation was on number 1. That was in the big long answer line. What property of matter did it illustrate? You gave me that one. And then somewhere you wrote down which law it was. Okay, when everybody's finished that, rise. Stand up. Okay, everybody finished? Still writing? Okay, let's come back here. Let me get my computer too. Now please don't be tempted to touch anything until I tell you to touch something, okay? I've had to redo the whole setup because somebody got carried away. Not fast enough. Okay. All right, I'm going to try to yell some so my computer will pick it up. I will need 2 volunteers. 1, 2. All right. So your hand first. Which place you want? This one. Okay. You'll have this one. All right. Now, don't do a thing till we get to you. Okay. What I want you to do is take the bottom thread. And by the way, I'll describe it. These are 200-gram masses suspended from threads, with threads hanging off the bottom. So, on this one, Ryan's going to take it, wrap it around his finger, okay, and then very slowly start pulling down on this thread. And keep pulling harder and harder, very, very gently. Can everybody see? Because you need to see this. Pull very, very gently. You can go on the start. Very, very gently, but increase your pull and increase the pull. What I want y'all to notice is which string breaks first. Oh, I need someone stronger, I think.
I just lost the grip.
Okay. Oh, which string broke first?
The top.
The top. Okay, record that. Okay. It's destroying my gun. All right, good. Thank you. Okay. Everybody recorded. Okay. We got some trash over here. Well, it's not there anymore.
It was top. Thank you.
The top. Okay. All right. Now, what Mark is going to do is wrap it around his finger like this. But Mark, on the other hand, is going to have a lot of slack in the string. And then all of a sudden, he's going to do a real quick jerk downward. Very quick, and you tell me which string breaks first. Wrap it around your finger. Give it a lot of slack, 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 slack. Now pull sounds real quick. Whoa, which broke? The bottom. Okay. Now, let's come back to the first pull here. Explain why the top thread broke first rather than the other, the bottom. Anyone have any ideas?
It was suspending the 200-pound weight or 200-gram weight and the force going down.
Excellent. The bottom's thread only had the force of his pull. The top thread had the weight, which was a force, plus the force of his pull. So it had more net force pulling downward. Okay? So the top thread had more net force pulling downward. It had both the weight of the mass plus the amount of the pull. Sorry, there's no more horizontal surfaces sitting here to write on. Some of you are having to do vertical surfaces. Okay. Now, which of Newton's three laws best describes that then?
Is it the second?
Yes, the net force law. Okay, the second law. Perfect. Oh, good. Okay, all right, on Mark's over here, where he said the sudden jerk downward, explain why the bottom string broke, not the top.
The amount of inertia coming down when the pull had all the slack in it.
Okay. This mass has a certain amount of inertia. So it was staying right where it was with a real quick jerk, just like the pulling on the paper. The inertia of this mass kept the top string from feeling anything, if it could feel something, right? Because the inertia of the mass stayed right where it was. Okay? That's the second rule. Explain why.
What was the explanation? Because the weight.
The inertia of the mass. It's related to the mass and weight, but inertia of the mass kept this top string from sensing any pull whatsoever. Just like the mass on the table, when you jerked it quickly, it stayed right where it was. This one stayed right where it was. that pull down on this rainbow. Now, which of Newton's three laws best describe that conclusion? The first, the law of inertia again. Excellent. Y'all are good. Some other classes take a lot longer than this to figure those out. Okay. Now, it's going to take me just a little bit to set up the next part. So, I can go back to the main part of the lab, and I'll be in there momentarily. Lab bench here. I have scales and weighing pins. If you can get the balls to set on there without rolling off, you don't have to use a weighing pin, but if you want to, be sure you zero the scale either with the weighing pin or however you're going to measure. So one person come up and determine the mass of two of these balls, and another person, only do one ball. Ray, you've already volunteered. Let somebody else do something. Okay? We didn't volunteer before. Okay? We'll make you have time to do something else. Okay? Anybody? Got details? Come on, somebody. Okay, done. You're at the scale first. Jay's doing the small ball first. What is its mass? Second. 27 grams. But I want you to register that in kilograms. How many kilograms is 27 grams? Anybody? Second. 0.02, yeah, 1 kilogram, 1 gram is 0.0, 1 to 27 would be 0.027. Okay? And what do you have done for one of the large balls? Okay, and what would that be in kilograms? Where's my, wait. Everybody's here, but I forgot to bring in my computer. Wait, say that again?
0.27.
3 decimal places, but 0.027. Okay, and what was yours? 64? Is that what you said? How many kilograms would that be?
So another 0.026.
Say that again?
Yeah, 0.0.
Yeah, 0.064 kilograms. Okay? Okay, someone else come and measure the large ball here. And someone else come and measure the second large ball there. Zero your scale first. Take it back them off, I'll hold it if you want me to, so you won't do it. Okay. Zero to scale. Just that way.
About 70.
Huh?
This one's about 70.
About 70?
Looks like 68.
Okay.
0.068.
068? Yeah. 1068, what's yours? 1064. Okay, the three large balls are all fairly close to each other. 1068, 1064, 1064. Okay. Now, I'm going to do the honors here. I might need a couple of qualified ball catchers, okay, to get this. This isn't going to be too bad, but let's try it. What it says to do is with one large ball stationary on the track, there it is, roll another large ball toward it at a speed of about 1 meter per second. I don't know what a meter per second is, so I'm just going to sling it, okay? We'll call it a meter a second, okay? Now, immediately after the collision, describe the motion of the two balls. Now, why I say immediately after the collision, maybe something happens right at the collision and later something else happens. Describe what happens immediately on contact. And I'll explain why in a minute. So I need a ball catcher over here. Oh, you've already done something. You can do it. Okay. All right. You think he's skilled. Okay. All right. Now, I'm not all that good of a ball swinger here, so this is going to be, now y'all, can y'all see the ball? Stand up if you need to. Don't let me get in the way. Okay, I'm going to go this pretty fast. And when y'all are ready, let me know it. You ready? What happened right at contact? Okay, put it back here again. Look at what happened right when it hits. Right when it hits. Whoa! It hits it. Okay? Ready? Right when it hit it, it stopped. Okay? And then it picked up the roll again. Now I'll tell you why that happened. If I had greased the ball and the rack really well, so it slid down there, that would have been linear momentum. But as it was, it rolled because there was some friction, just a little bit. And since it was rolling, it had a little bit of what we call rotational inertia, rotational momentum. That's why it started rolling after. But right at first, it was just the linear momentum. So that's why whichever one you call the first ball, this one stopped and that one kept rolling, or started rolling. So you describe that however you want. You name which ball is ball one and which is ball two, whatever. You got it written already? Okay, let me know when you're done writing. Okay. Approximate the momenta of the two balls before the collision. Okay, which one did y'all call ball one? The one that I rolled? So what was its initial momentum?
1 meter a second.
Whoa, I thought that was the velocity. What is the momentum? Anyone remember? Newton's quantity of motion. Remember what that was? I did have my recorder on that. Remember what momentum is? Mass times velocity. Mass times velocity. So what was the momentum of ball one?
1 times 1 is 1.
What, 0, 6, 4, 6, 8, whichever one you take that to be.
Times 1.
kilogram, yeah, times 1, which would be 0.068 kilogram meter per second. That's the unit for momentum. Kilogram meter per second. There's not a special name unit for that. What was the initial momentum of ball 2?
Stationary.
Second?
Stationary.
Yeah. So what?
Zero.
What was it? 0, because it had 0 velocity. So what was the initial momentum of the system? The sum of those two, which is 0.064 kilogram meter per second. Right? Didn't need your calculator for that, did you? Or a picture. Okay. Now, you tell me approximately what was the momentum of the ball after it hit. This one stopped and went to 0. What did the other one do?
Contracted.
And it left at just about the same speed, so it would have had just about the same momentum. So does it look like the momentum of the system was conserved? Yes, it did. All right, good deal. Now, this time I'm going to put 2 large balls on the track. And I'm going to roll 1 toward it. I seem to have lost.
Straight ahead.
Oh, there it is. Okay. All right. My ball catcher in place. But before I do this, I'm going to roll 1 toward those 2. I want you to tell me what you think is going to happen. Make a prediction here. Let me close the door because I know I'm bothering you.
The first ball is not going to move from the last ball, like the one on the far right.
Okay, that's what he says. Anyone want to come up with a counter to that? Okay, you feel like he's close to right. Well, let's see what happens, especially right at a collision. Okay, look at that. This ball, Roger's ball. However you want to describe that. You can name them 1, 2, and 3, however you want to. You describe that. Would you say that the momentum of that system was conserved? Yes, because the third ball, or whichever one you call that, took off and went at just about the same speed as the first ball. They were almost the same mass. So yes, it looked like the total momentum was conserved. All right. I'll go back to 2 balls. This time I'm going to roll them toward each other. This is kind of hard for me to do because I'm left-handed and I tend to roll harder with my left hand than the right. So I try to compensate and then overdo it. So I might need a ball catcher at both ends. So, okay. Now, since I'm rolling this one supposedly at 1 meter per second, this one at 1 meter per second, what's the total momentum of that system? Velocity.
Point. No, 6.4, 6.82, 6.8, twice.
Okay. What kind of quantity is momentum? No. What kind of quantity is momentum?
Should be 0.
A vector quantity. So if this one's positive that one's negative that, what's the total momentum?
0.
Very close to 0. Okay? So what do you think is going to happen? Okay. And then will the momentum be conserved? Huh? Okay. So you think which way?
Whichever one's rolling fast.
Okay. Let's see. Let's observe what it is. I'm going to try to do them at the same speed. What you reckon?
Equal and opposite reaction.
Okay. Now, this one now had the positive momentum. That one had the negative, so still added to 0. So, good deal. All right. So you answer that however you want to. You don't have to answer about momentum. That was just thinking through. This is number H. Putting one of the large balls on the track, as it said, and we'll roll the small ball toward the large ball. I'm going to try to do about 1 meter per second. I want you to describe the motion immediately after the collision. Anyone want to make a guess of what's going to happen?
Slow down.
What?
The big ball is going to slow down. The small
Well,
ball.
it's at rest now, so it's going to slow down.
I think it's not going to carry all the energy. It'll carry all the energy into it, but it's not going to roll as fast as the small ball. So it's going to more.
Okay, well, the small ball.
I think the small ball will bounce off and go through.
Okay, so we have small ball bouncing off and the large ball moving slowly forward. Okay, that's the guess here. Anyone want to make a counter suggestion? Okay, let's see what we get. All right, here we go. Oops, I'll move you. Okay, now notice I'm putting the large ball this side. The reason I can't do that on this side is because the small ball hangs down too far. So I put it right here. Okay, here we go again. Yeah. This one did bounce off, and that one moved slowly forward. Now, here's the bizarre part of that. The large ball left with more momentum than the small ball had to begin with. Agree or disagree? How do I know that? Because the small ball now has a negative momentum. For momentum to be conserved, that has to have more this way than that way, because all the momentum was small ball to begin with. So this one has to have more momentum that way because small ball now has negative momentum that way. Yeah. You don't have to put that one down. Just describe what happened. Now, this time, I'm putting a small ball in the middle. No large ball or small ball. Did everybody finish writing? I don't mean to rush. Everybody called up. Yeah, everybody was. Okay. Now, any guess of what's going to happen now?
The small ball's going to fly forward.
Okay, fly forward. Okay, take up the okay, and the big one's going to keep rolling that way. We think at a slow speed. Now, again, pay attention to what happens right after the collision. That's what's important. Okay. Ready? Sure enough, small ball took off faster.
Carries it with it.
Yeah, the large ball did catch up. So that's because of its angular momentum. Linear momentum, it was this one left faster and this one followed it just a little bit weaker. Okay. That's because the large ball had so much more momentum that it gave a lot to the small ball, but kept quite a bit. Now, here's another one. I'm going to add to it. You can either write it the margin at the bottom or turn it, flip the page over right on the back. I don't care. But before we had two at rest, rolled one toward it. Now I'm going to try to roll toward to one at rest. So what do you reckon is going to happen here? I'm going to roll two balls toward one at rest. So what do you reckon the result is?
Two outside are going to go opposite way.
Okay, and
The center one's going to stop where the contact point is.
Okay. I heard that these two are gonna move that way and this one will stop, is that right?
No, they're gonna, this one's gonna go this way, that one's gonna go that one, that one's gonna stop at the time.
Okay, let's see, any other counter suggestions? Okay, let's see what happens. Later I'll get you to explain the momentum of that to me. Okay, ready? Oh, what happened? Yeah, these two went, that one rested. Why? Momentum was conserved. We had two ball coming in, one at rest, so when they left, two ball left, and one was at rest. Momentum was conserved. Right? Okay. That's either on the bottom margin or the back of the page or somewhere. That's two flying into one. Any questions on these? Did this make any sense? Was it helpful? And the bad news is, that's all there is to what? I'm sorry. Hey, don't throw anything at me, okay? You think you're not getting the money for it, aren't you? I can tell what you think. But there's no refund. Work on whatever you need to do to get it written up. You can either Absolutely. I'll try to make up and have a real long lab next time. No.
You got test Thursday, right?
Thursday, yeah. We'll have, and the test on chapter 2 is Thursday, and we'll have the first lab on chapter 3 right after the class. So 2 hours of class, 2 hours of lab, 30 minutes of test. Still moving furniture, huh?
Yes, sir.
All right, good deal. We have cleaned out my wife's grandparents' place after her grandmother died. I can't believe how much stuff they have.
Yeah.
I mean, attic full.
Where could I get the stuff that we did for the second lab and the first test?
Okay.
Because I think I'm the one that's supposed to.
Yeah. Yeah.
2 months ago.
Yeah. I can't hold her load. Well, Mom has 2 sisters, and they're gonna help her, so we're all moving on.
Yeah, you're missing. Missing first. No, you got the first lab.
No, I think it's the second lab and
First test and the second lab.
Yeah.
Right.
Where could I get those? Or how do I?
Okay, I can give you the second lab.
Well, I have the second lab.
Oh, you
but
do?
can give me a copy. But the
Okay.
test, I didn't even know where it was.
Okay. Yeah. Anytime you want to take it, like if you want to take it right now, you can. But if you don't feel ready for it, you can.
Well, I don't know what's on. Is it
It's on
chapter
chapter
1?
1. Yeah.
Oh, okay. Well, I don't have the book, so I guess because I thought the check that we pick up from the cashier's check, they told me that it's not here, it's the one in Birmingham, so I have to run to the Birmingham campus and get it.
Oh wow.
And then the book there or here.
Right. No, it won't be there. It'll be here.
Okay, well,
They
here.
don't teach physical science over there.
Okay, well, I'll buy it from here and have to study a little bit.
Okay, yeah. Well,
And I'll let
whenever
you
you're
know when I'm
ready,
ready.
let me know.
And to find what we did on the second lab, did you record it or how did
I recorded as much as I could, but you see,
Yeah.
it wasn't like today's lab. It's, everybody was doing their own thing.
Right.
You know?
So where
And
can I get the information for that?
Yeah. If you want to get with me sometime during my office hours, either before class or after class, like now, and then take the measurements yourself, you can.
Okay, I'll take it before, because
Okay.
I have a Thursday class I get out at 2,
Mm-hmm.
and I can do it from
Okay.
2
From
to
2 to 3:15.
Yeah.
Okay. All right. Well, you know where my office is?
Yes, right here down the.
Yeah. Right.
Yes, sir.
And then so come on by, and then we'll. There may be a class in here, but we'll quietly get it and go somewhere where you can take it.
Yes, sir.
Okay.
All right, appreciate it.
Uh huh.
Have a good one.
You too. Thanks.